get started. Okay, let's see. We will take a look at gradient descent today, okay? And so, we're, this is a little bit of a detour because we'll get back. So on Monday, we talked about cross-validation as a way for method model selection. And then on Friday, we'll talk about regularization as a way to kind of control your the variance of estimates. And today we're going to look at gradient descent, which is going to show us, how we can minimize or optimize some kind of function here. Okay. And so, we've been talking about this loss function, and we're saying, as far as linear regression goes, we want to find the set of parameter values that will minimize the loss function. We want to minimize the mean squared error. Okay, and that's what we've been saying. Right? And again, I know you guys are familiar with the linear regression, but this is kind of it's going to serve as a good starting point before we move on to something slightly more complicated models. Okay, so we want to minimize the mean squared error, and what we've been doing so far is we've been doing a bit of calculus. We calculated the derivative, we set it equal to 0, and we solved. We did this. We can do it with partial derivatives. We can also do it in matrix notation or vector notation. Okay. Sometimes, however, the loss function that we're working with can become more complicated. It can be more complicated than just kind of this sum of squared values. And in those cases, you might be able to figure out the derivative, but then trying to solve for where the derivative is equal to 0 might not be an easy thing, okay? And so we can rely on computational methods that can be used to help us at least find a local minimum, right? Finding global minimums sometimes is difficult, but computational method can help us find a local minimum, and then maybe if you run it a few times with different starting points, you might be able to find different local minimums, and among those, pick the one with the best performance and pretend that that's going to be good enough, right? A lot of times we're just going for good enough. We're not actually, again, all models are wrong, some are useful, and so in a lot of cases, we're just looking for good enough, okay? I don't know if that's the best philosophy about everything in life, but sometimes that's all we want to hope for here. Okay, so we'll take a look at some computational methods for multi-dimensional optimization, which is basically pretty much all of our problems are going to be multi-dimensional in nature. Okay, and so we want to find, the parameter estimates. In our case, for linear regression, we want to just find the slope and the intercept. That's still a multi-dimensional problem because you've got two values there, right? You've got the slope and you've got the intercept. You've got two values to optimize, right? And so we're going to treat the data as fixed. We only have, in this case, we only have two parameters, right? But if you got a more complex model, so I think next week we'll just take a look at very simple neural networks. Even with a very simple neural network, you might have something like 17 parameters to estimate or something like that. Okay, and so here we will look at gradient descent in 102A. At least in my class, we covered coordinate descent. Those of you who are in Professor Wu's class, do you guys also cover coordinate descent in 102A? Maybe, I don't know who is here from the other professor's class, but anyway, we'll take a look at gradient descent. Okay, and so we talked about the gradient on Monday. Wait, right? No, on Friday of last week. Okay, we talked about the gradient, and the gradient represents kind of the slope of the tangent line. Or I'm sorry, for the derivative represents the slope of the tangent line to some function, right? You've got some kind of function, and then the derivative is the slope of the tangent line, okay? And the kind of the multivariate equivalent of that would be the gradient. And we saw this on, I believe on last Friday, where we said, the gradient is the direction of greatest increase for some function at x, right? So if x is some value, some vector in 2 dimensions, the gradient is going to be another vector in 2 dimensions that will say, this is the direction that you need to go for the amount of greatest increase, okay? And so, so basically you can think of the gradient, if you're standing on, think of standing on some kind of hill or some kind of surface, okay? Maybe not the top of a hill, but you're standing on some kind of surface. The gradient is basically an arrow that points uphill, okay? So basically you're gonna find the gradient, it's pointing uphill, and you're gonna just say, I don't wanna go uphill, I wanna go downhill. And you just take a step in the direction opposite of the gradient, okay? So if you move in the direction opposite of the gradient, that's going to be downhill. And effectively, you just take a step and you keep saying, well, which way is uphill? I'm gonna move in the direction opposite of uphill. And if you keep doing this, you'll eventually get lower and lower and lower, and you'll eventually reach maybe the bottom of some kind of valley. All right. And that's basically the idea of gradient descent. And you can almost think of it as taking like a ball, setting it up on a hill, and it's just going to roll downhill. And that's basically all we're doing with gradient descent. We're just taking a ball, we're going to just let go, and it's going to just roll downhill. Okay. And so the entire algorithm for gradient descent is about as simple as algorithms get, okay? There's like calculations that get involved, and calculations can be a little bit messy, but the algorithm itself is very, very simple, okay? We're gonna say we are currently at some location W, okay? So we're gonna say our location is at some vector W at time n, okay? So if we're at time n and our current value is W, the next value, W at time n plus 1, is going to be our current location minus, and this thing represents the gradient. So this is nabla f of Wn. This just represents the gradient of the function, our surface or our hill or whatever we're talking about. It's the gradient of it at location W. So we're going to just do the next location is going to be our current location minus some constant, the scaling factor gamma or lambda, okay, some scaling factor times the gradient. And that's it. That's the entire algorithm. Take your current location, subtract off some constant times the gradient. And so I'll illustrate this. Okay, so we're gonna, this is basically it. We could end the lecture here, but I'm going to show you a bunch of examples to hopefully, so that this will make a little bit more sense here. Okay. Maybe it already makes sense and the rest of the lecture will be boring for you, but let me give you your first quiz answer for today. View quiz answer is E as in elephant. E as in elephant is first view quiz answer for today. Okay, so let's just try this out on some arbitrary two-dimensional function. Okay, so I got x1 squared minus 2x1 minus 0.5 x1 x2 plus 2.5 x2 squared. Okay, that is the function, and the gradient of the function is, I'm just going to do this using calculus to find the gradient. The gradient is going to be a two-dimensional vector. And it's going to be basically the partial derivative of the function with respect to x1 and the partial derivative of f with respect to x2. Okay, and so if I say, okay, what's the partial derivative of this with respect to x1? Well, x1 squared becomes 2x1 minus 2x1 becomes minus 2. This is minus 0.5 x2. And then this is 0 because there's no x1 term. Okay, what is the partial derivative of this with respect to x2? This is 0, this is 0. This is negative 0.5 x1, and this becomes 5 x2. All right, so this is, this is the gradient of the function in two dimensions here. Okay, so this is kind of a contour plot of the function. It's basically kind of like a bowl. You can think of it as like, I don't know, like some kind of smooth ellipsoid bowl. So you just, I don't know, think of what has an ellipsoid shape in real life? I don't know, like the bottom half of an egg or top half of an egg, if you flip it upside down, kind of looks like an ellipsoid, but maybe but maybe a little bit oblongish. Okay, so all right, so this is kind of what it looks like, and here we have contour lines. So if you kind of just slice it across, you get something like this, right? And so we can kind of eyeball it and say, all right, the minimum, like somewhere around here. I don't know what's that, 0 point something. Okay. Here's what it looks like in 3D, and I could have used some kind of plot thing to have it revolve in 3D, but this is basically the thing. Okay, and so this is what we will do. We will calculate the gradient for a point, an arbitrary point. We're going to just start off at -5, 4. So in our plot, this is kind of, I think -5, 4 is going to be like up here. Okay, we'll start up in this corner. And we want to say, all right, which direction is uphill, which direction is downhill? So uphill is going to be in this direction. We're going to go in the opposite direction. So we're going to basically take a step in this direction here. Okay, so we would calculate the gradient at this location. So we're going to put in -5, 4, and we're going to plug that in to calculate the gradient at f. And so this is going to be the gradient at this location is going to be a 2-dimensional vector. And so I just plug in -5, 4. And so I do into the first partial derivative, I plug in -5, I get -10 minus 2 minus 4 times 0.5. So I get -14. Over here, the other thing, I get -0.5x. So I get -0.5 times -5, and then 5 times 4, 20. And so I get 22.5. That's going to be our gradient at f. Okay. And then so as far as the gradient descent algorithm goes, we're going to take our current location, which is -5, 4, and we're going to subtract some constant, okay, gamma times nabla f. All right. So here, I just arbitrarily have gamma set to be 0.1, and this constant can be any positive value. So anything greater than 0. So here it's 0.1. You could have a gamma of 0.01 or gamma of 10 or something like that. It doesn't, well, it matters, but it depends. What gamma you should use depends on the problem. Okay, so here we're going to do -5, 4, and then we're going to subtract 0.1 times the gradient here, which is -14, 22.5. So 0.1 times -14, 22.5 becomes -1.4 and 2.25, but I'm subtracting it. So I'm going to have -5 plus 1.4, which takes me to -3.6. And then I've got 4 minus 2.25, and that takes me to 1.75. Okay, and so if I plot this, -5, 4 is here, and the resulting spot is going to be -3.6, 1.75, which will go from here over to here. Okay, so this is -3.7. What did I say? -3.6 and 1.75 is going to be this coordinate here.
How do you find the initial points, -5, 4?
This is arbitrary. I just arbitrarily selected -5, 4. This is not, there's no, I picked that because it happens to be in the bounds of my window that I plotted. Okay, just to illustrate this. Okay, because so basically the idea is you don't know where you're starting, right? The idea is we want to find the location that's kind of the local min, or at least, you know, some kind of local minimum, and we don't know where that local minimum is, so we just start somewhere. So I just arbitrarily said, let's start off here at -5, 4, and we're going to use gradient descent. And basically gradient descent is the algorithm that just says wherever you start, follow these directions, and that should get you somewhere. Okay, and the direction is basically how do you get downhill? And the gradient descent algorithm is wherever you start, ask which way is uphill and move in the opposite direction, right? And that's the entire algorithm. Wherever you're starting, like if the answer is I want to find downhill, you just say which way is uphill and move in the opposite direction, right? And it sounds silly, okay? It sounds silly, but that's basically what we're telling the computer, okay? So you're giving it some starting location wherever you are. You're going to say which way is uphill. That's the calculation of the gradient, and we're going to say just move in the opposite direction of uphill. okay? And when you do that, we're going to end up somewhere over here, okay? Computationally, this is what it might look like, okay? So here I'm going to say, all right, well, I'm going to write a function for f. And I know this is not great R style where I put the function in one line here, but we're going to say the function of f is, x1 squared minus 2 times x1 minus 0.5 times x1 times x2 plus 2.5 x2 squared. And then the gradient of f is going to return a vector of length 2, okay? And the two components that it's going to return, the first one is basically the partial of f with respect to x1 is going to be 2x1 minus 2 minus 0.5 x2. And then partial with respect to x2 is negative 0.5 x1 plus 5 x2. Okay, so here I write the functions to kind of code this up. And then we're going to start off just an arbitrary starting location of negative 5 comma 4. My gamma is 0.1. And so if I plug in my starting location, start 1 and start 2 into the gradient of f, I get negative 14 and 22.5, which is exactly what we calculated here. And then basically our next location is going to be the starting location minus gamma times the gradient. And so if I do 0.1 times this and I subtract that from my starting location, I'm going to get negative 3.6 and 1.75, which matches basically the math that I did over here. Is that all right? Basically writing this into R. Okay, so I've done that, and this is basically one iteration of gradient descent. We just started over here, negative 5 comma 4. We took one step, which is downhill, and I end up right here. Okay, and so if I do this again, I can say, all right, so now I'm at negative 3.6, 1.75, negative 3.6, 1.75. We're going to calculate the gradient here. The gradient at this location is negative 10, comma 10, negative 10.075, comma 10.55. And the next spot I take is going to be take my starting location of negative 3.6, 1.75, and basically subtract this off. So this says this is, if you want to go uphill, you want to go 10 to the left and 10 up, and we're going to go in the opposite direction. We want to go down and to the right. Okay, and if you do that, that takes us to here. Okay, and so let me plot that. And so the next step says, okay, if you want to go uphill, that would point in this direction. We're going in the opposite direction. So we end up right here after 2 iterations. And we basically just repeat this. So I'm going to just run a loop. Okay, and so this is basically the entire gradient descent algorithm. All right. I'm going to say, take your current location, your x vector, store that in this matrix locations in row I. And then the next iteration, update your x vector to be your current vector minus gamma times the gradient of the vector. Okay. And so I run this. And so this is pretty much it. I'm going to run 20 iterations of this. Okay. And then here, just to plot it, I'm going to run iterations, some arrows here. And this is what it looks like. Okay, so I started off here, and we go downhill, and we go downhill, we go downhill. We keep taking steps, and we can see the steps get smaller and smaller and smaller. But I'm just basically rolling the ball downhill, and we end up after 20 iterations. We're not totally in the middle, but we're getting pretty close to there. Okay, is that okay? And so here I arbitrarily selected gamma to be 0.1, okay? We could select different values of gamma, okay? So here I could choose a smaller gamma of 0.03, and basically it works kind of the same, except my steps are smaller, and so you're just, you're taking, it'll take you longer to get to the bottom. Okay, so generally we recommend start off taking small steps and then increase the step size. Okay, so taking small steps, that's fine, that's safe. It just might take you longer to get to the bottom. Here is bigger gamma. Okay, with gamma set to 0.15. I'm taking bigger steps, but I still get to kind of get to the bottom just a little bit faster. But if I take gamma to be a little bit too big, 0.3, okay, this actually, we're okay. But we get this funny pattern going on. Okay, what's happening here is we're basically, our steps are too big, okay? So we say, all right, you know, imagine you're kind of on the hill and, or I don't know, there's like this valley, right? You're trying to get to the bottom of the valley and you're on this side of the hill and you say, okay, well, which way is uphill? This way is uphill. So we want to take a step in this direction, okay? But you take such a big step because, so you're not actually walking, you're like teleporting, right? And then so you take such a big step, you actually end up on the other side of the hill or other side of the valley, right? Because it said, you know, which way is downhill? We say, oh, downhill's in that direction. And then you say, okay, well, let's just hop a really big distance in that direction. And you end up hopping so far that you end up on the other side of the hill. And then so we end up going past the kind of the minimum and we end up over here and we say, oh, okay, well, which way should I travel? We're going to travel that way now, okay? And so now you end up getting this kind of zigzag thing, right? This we still end up getting towards the bottom, okay? Sometimes, however, you take, what happened here is your steps get too big that you can end up actually overshooting and you'll fail to converge. So what's happening here is, you know, imagine you're on this valley, okay, and you're on one side of the valley and you say, okay, which direction do I need to go? And you say, okay, well, we need to go in that direction. So we started off over here and we say, okay, we need to go in this direction and over here. And not only do you kind of take a jump, but you jump so far that you end up on the other side and you end up actually farther away from the bottom, right? So let's say, you know, you started on the valley and maybe you're at, I don't know, let's say the bottom of the valley is at 0 and, you know, you started at 50, okay? And you take a step on the other side that you end up actually higher up. You end up at like 70 on the other side of the valley, okay? And every time you get higher up, basically the gradient gets bigger, right? The gradient is going to get steeper and steeper and steeper. And so what ends up happening is you end up taking even bigger steps. So you start off at 50, you say, let's go in the other direction. You end up on the other side and you end up higher and you're up at 70. And you say, oh, okay, well, we need to go in the other direction again. And so you say, all right, let's jump over here. But then you end up even higher and you end up at like 95. And you just keep getting higher and higher and higher and higher. And so you end up overshooting and you don't converge, right? And that can happen just based on your choice of gamma, okay? So what are you supposed to do with gamma? We often just say start small and then just try increasing it a little bit at a time. And eventually you might break the thing. And when it breaks, you say, okay, well, that's too big. All right, so let's take a look at how gradient descent would work for least squares regression. Okay, so we'll use gradient descent for least squares regression. Before I do that, let me go ahead and give you your second quiz answer. Second quiz answer today is A. A as an apple. A as an apple is your second view quiz answer for today. Second view quiz answer. Okay, so for OLS regression, our loss function is this in matrix notation, okay? It's T minus XW transpose times T minus XW, okay? 1 over N to make it the mean squared error, okay? And we want to just find, some kind of minimum here. All right, and so we can do the partial derivatives, and this will work, okay? Or we can do take the gradient in matrix notation, right? So I don't know if I want to bother stepping through this line by line, but you can go through this on your own time, and this is what you would find if you wanted to find the gradient. So basically, the partial derivative of the loss function with respect to the intercepts, which is W0, and the partial derivative with respect to the slope, which is W1, would give you kind of similar, would give you these results. Or if you take the derivative with respect to w in terms of vector notation, this is the result that you would get. And I think I've shown you the steps for this on Wednesday or Friday's slide of last week. Okay. Okay, so basically in non-matrix notation, we would take kind of our values and we would subtract off gamma times the vector of partial derivatives. And in matrix notation, we would take our current vector value w, and we'd subtract off gamma times the gradient of f at w. Okay, and when we do that, we would get the next value here. Right, and so this will work just fine. And so here I'm going to just start with this very simple example. Okay, and so I have 3 data points, 1, 3, 5, and the coordinates and the actual values are 4.8, 11.3, and 17.2. And the optimum solution is an intercept of 1.8 and a slope of 3.1. Okay. And so here we have, this is the results of the gradient with not the result for the intercept and slope using LM. Okay. Question, what is the purpose of gradient descent here if we have closed form expressions for W0 and W1? There's no, we would not do gradient descent in this case because we do have closed form solutions for this, right? So I'm just starting off with something where we know the answer. Basically, what I'm trying to show you is that gradient descent works, right? So we already know the answer. We know the answer because we do have closed form solutions for the intercept and the slope. We can get the answers using LM. We can get the answers using any of our closed form solutions. But what we're going to do is I'm going to just start off at an arbitrary location, and then we're going to run gradient descent, and we're going to see gradient descent give us the result that we want. Okay. And this is actually, I recommend doing something like this. Anytime you try out something new and you're not quite sure if you're doing it right, because that's an issue that you will run into, is that you'll say like, okay, here's a new technique and I want to see if I'm doing it right. Pick a solution, pick a problem where you already know what the answer is, right? You say, well, I know for this problem, I know the answer should be this, and I want to run this new technique or new method. And if your new technique and new method gives you the answer that you know you should be getting, then you can be like, okay, at least I know I'm kind of running this correctly, right? So that's all we're doing here, right? I'm just starting off with an example that we already know the answer to. The answer is this, and we're just hoping we get the same answer by running gradient descent, okay? All right, and so this is what the answer would look like if we plot an intercept of 1.8 and a slope of 3.1. This was kind of what the plot would be for these plots, 1, 3, 5, 4.8, 11.3, and 17.2. Okay, so here I'm going to do it with matrix notation. The algorithm just says take your current location, subtract off gamma times the gradient, and your next value to use that. Okay, and so here we have the gradient at W. The gradient of f at W is this, right? And so here we're going to say, okay, the gradient is going to be with respect to W is going to be X transpose. So here I have negative 2 over n here times 2 over n. I'm going to just go ahead and drop this constant, okay? Because, I mean, the constant does matter, but because I'm going to be multiplying it by gamma, okay? What if I get rid of it here, it's just going to increase gamma by a factor of 2 over n, or I guess n over 2, okay? It's just going to affect basically the scaling value of gamma that I should use. So I'm going to just go ahead and drop it. So I have X transpose T plus X transpose XW, okay? So here I've got, I'm sorry, negative X transpose. So I've got negative X transpose times T plus X transpose times X times W, okay? And so this is going to be the gradient, and this is going to accept some kind of vector W, and this will return a vector here. Okay, and so here we're going to just start off arbitrary starting location for the W vector. I'm going to start off with an intercept of -1 and a slope of 1.5. Okay, we know that the optimal solution for W is going to be intercept of 1.8 and a slope of 3.1. And I'm starting off with the wrong values of -1 and 1.5. Okay. Our gamma is going to be 0.02. Okay. I'm going to just choose a small one. Okay. But, and hopefully this will work. And then I'm going to just run the algorithm like 1,000 iterations. Okay. So I start off with my gamma of -1, 1.5. And I'm sorry, start off with my W with this location, and we're going to just say keep updating W. So here, all I'm doing is this. I'm not keeping track of anything so far. And so I just do W vector minus gamma times the gradient, and we update the W vector as such. And after 1,000 iterations, it says the resulting W vector has values 1.79995 and 3.10001. Okay. So this is quite close, not exactly so, but it's quite close to the actual coefficients of 1.8 and 3.1. Okay. And of course, in real life, we would just use LM, or we would take the answers here. Okay. But here I'm just kind of illustrating gradient descent for a simple problem where we know the answers. Okay. And so we see, by running gradient descent after 1,000 iterations, we get something quite close to the true answer. I could run this even longer and we'd probably get even closer. But this is getting us something very close to the optimal solution. Is that all right? As far as just running the algorithm, this is the entire algorithm right here. Okay. And again, so gradient descent is very simple. And all we're doing is we just have to calculate, figure out how to calculate the gradient. Okay. And as far as ordinary least squares regression, figuring out the gradient, in matrix notation is not too difficult. You just have, X transpose T plus X transpose X times W, negative X transpose T. Okay. I want to show you a couple plots that show you kind of what's happening as it's finding as it's searching for the optimal solution. Okay. So again, the minimum occurs when the intercept is at 1.8 and the slope is 3.1. And this represents the intercept and this represents the slope. Okay. All right. So this is just code that I've written to kind of plot what's happening here. Okay. And so this is the path that gradient descent takes. Okay. So the solution is, this really weird shaped bowl with sides that are very steep. And so these sides are very steep and in kind of this direction. And so when we start off at this location where the intercept is -1 and the slope is 1.5, in the beginning, it starts by rushing to increase the slope to be much steeper until it gets to around here. I don't know what this is, a slope of around 3.7-ish or something. And it does increase the intercept, but then eventually it says, okay, now let's tone it down with the slope, and the slope becomes a little bit less to, 3 point something. Eventually the bottom is at 3.1 with an intercept of 1.8. And so every time it kind of tones it down and makes the slope a little bit less steep, it's going to start increasing the intercept. All right. And so visually what's happening when we're trying to fit our data or fit the 3 points in our data set, this is what it looks like. Okay. So visually, we started off with an intercept of -1 and a slope of 1.5. Okay. And so here are the 3 data points, and our initial line of fit has a intercept of -1 and a slope. This red line has a slope of 1.5 here. Okay. And so at the next iteration, we're going to kind of take a step opposite of the gradient, right? And so at the next iteration, it says, you know what, this is doing a terrible job of fitting the data points, okay? What we need to do is we need to increase the slope, okay? Increase the slope. And so, so at the next iteration, the slope goes from 1.5 to 2.3. It says at the next iteration, increase the slope. And so it increases the slope. It increases the intercept to say -0.7, and this is the line. So this is still doing a terrible job of fitting our data, okay? And it says, and that's what this coordinate represents, right? So this represents the coordinate of this intercept and the slope, and this is what the fitted line, right? So every location on here represents kind of a different fitted line, right? You can, if you move up and down in this direction, you get a steeper slope or more shallow slope. And if you move it left or right, you're raising your the line up and down, okay? So here we've gone to here, we've got a steeper slope, okay? After 5 iterations, okay, the slope is now at 3.33, okay? And the intercept is at negative 0.45, okay? And so this is what the resulting line fits, right? So just after a few iterations, this is where we started off. We can agree that this is a terrible line that fits the data. After a few iterations, this is doing a much better job as far as how close the data fit the fitted line, or how close the line fits the data, right? So this line is a little bit too steep, but and we have a slope intercept here. And so after a few more iterations, at 15 iterations, we have a slope of 3.63 and intercept of negative 0.23, right? And so now the amount of kind of adjustment that happens is going to be a little bit fine-tuned. We're going to take this this red line, and maybe it's a little bit too steep. So what we're going to do is we're going to kind of make it less steep, but to kind of have it do a better job, we're going to make it less steep, but we're going to have to bring up the intercept to be something a little bit higher, right? And so after a few more iterations, after the step size gets a lot smaller. So from 15 iterations to 100 iterations, this is basically the amount of adjustment that happens. We're going from something a little bit less steep, and we're increasing the intercept. And after a few more 100 iterations, this becomes less steep, and we're increasing the intercept. And this is, you know, eventually we're going to get somewhere down here, but we're basically adjusting the slope and intercept of the fitted line, and we want to try to adjust the line there, right? Does that kind of make sense? What's happening? The relationship between this graph. This is a graph of the contours showing where we're looking at intercept and slope. It would be really cool if we had like an interactive thing here. But so this shows the intercept and slope, and this shows the kind of the fitted line here. And effectively, we're trying to find the location for this thing that's going to give us the best line, right? And the best line we know is this solution of basically 1.8 and 3.1 as far as the intercept and the slope, okay? And so you'd have to run it for, you know, probably another few hundred iterations, and eventually you'll get there, right? So gradient descent is not exactly a fast algorithm, but a lot of times it works, okay? And it's not even guaranteed to work, okay? So the reason why we like gradient descent is because it's very simple. It's simple to implement, it's simple to understand, but it's not fast, and it's not guaranteed to work. So pros and cons, okay? That's what you pay for the simplicity. Here is what could happen if you use a gamma that is too big, okay? A little bit too big. It still gets you to kind of the minimum here, but you can see that as far as the vertical axis represents the slope, okay? So one, it says, you know what, your slope is too shallow. So what do you need to do? You need to increase your slope. But now you've increased your slope too much, okay? It says, oh, too much, that's in the wrong way, okay? So make it shallow, and then, you know, you make it shallow, and you say, oh, too low again. And so now, you know, it's kind of this back and forth thing, right? This represents a little bit more control, like just keep increasing, and then we're trying to fine tune. But here it just says, you know, make it bigger, oh, too much, make it smaller, oh, too much, you know, make it bigger, and so you have this kind of back and forth business going on, okay? Here, this is kind of the opposite problem, where you're overcompensating, and you're overcompensating by like way too much, right? So this is kind of like, you see, you know, so I think they have like animations of like, in some video game, you're driving your car and you're going the wrong direction, so you steer the other way or the other way, and you just end up losing control. And that's what happens here. Okay, is we actually started not too far off, but the correct slope is not too far off, but we're taking directions in the other way, and so it just gets getting bigger and bigger and bigger. So as far as the intercept goes, we get close to the correct intercept value, but as far as the slope goes, it's just all over the place. So that can happen as well. Okay, and so as far as picking your gamma, pick an arbitrary gamma, but be ready to kind of mess around with it. Is there a way to know what gamma you should use? And the answer, unfortunately, is there is not a great way to figure out what the best level of gamma it is, right? And so there is a lot of kind of guessing and checking and figuring out, as far as getting your gradient descent to work, a lot can be kind of tied to the learning rate. And there's some ideas as far as picking the ideal learning rate, but it depends heavily from one problem to another and the values that are being involved. And so so it often has there's just a lot of guess and check here. Okay, let me just talk a little bit about numeric gradient calculation and checking. Okay, and so in our example, it wasn't too hard to figure out the gradient via calculus. Okay, or even using vector calculus. But a lot of times you'll be in a situation where maybe calculating the gradient wasn't so easy, and maybe you did it, but you're just not confident in your answer. Okay, and this is a common situation where you do the math, but you just have this little feeling that you're like, I'm afraid I did this wrong, right? And you want some way to just check, like, did I do this correctly, right? And so one thing that you can use is something called numeric gradient calculation. Okay, it's very simple. Okay, and so it's not and it's a bit inefficient. Okay, so you generally don't want to do numeric gradient calculation as your primary means of estimating gradient. You could, but it would be really inefficient. So what's recommended is try to find the gradient using calculus or analytically, and then verify that your gradient is correct by running a numeric gradient check. Okay. And so the way we do numeric gradient checking is we're basically going to take the definition of the derivative, which is basically that the derivative is you add a little kind of small value here to x, and you kind of just say, well, how much did the function change when I added a small value of h to x, and I calculate the value of the function there, and I subtract off the value of the function at x, how much did it change? Okay, and we're basically going to do that, but multi-dimensional. Okay, and so here we're going to just take and say, you know what, the gradient is basically a bunch of partial derivatives, okay, kind of tied together in this vector here. And we're going to just say, let's estimate the gradient using the partial derivatives by adding on a small value h to x, okay? And so first we want the partial derivative of f with respect to x1. So we're going to add a tiny value h to x1, all right? And we're going to say, how much does the value of the function f change when I add a tiny value of h to x1 versus leaving x1 at the starting value, okay? And in this case, for the partial derivative with respect to x1, x2 remains fixed, okay? And then just the opposite is true when we're doing the gradient partial derivative with respect to x2. We leave x1 fixed. x1 does not change, but we're going to add h to x2 over here, and we leave x2 over here as the original value. Okay, so so first we have to figure out, well, what is the value of the function at x1 and x2? So if you recall kind of the arbitrary function from, like, where was it? Way back here. Okay, this arbitrary function, and we say, well, what's the gradient with respect to this? we're going to calculate just at -5, 4, and we're going to say, okay, well, what is the value of the function at -5, 4? I just plug in -5 and 4 into this, and if you plug in all of the values, we're going to get 85. Okay, and we say, okay, well, what would happen if I add a small value to 5? What would happen if I add a small value to 4? Okay, and so remember, when we want the gradient, we want two partial derivatives. So first, we're going to add 0.01. Okay, just for illustration. Normally, you'd add something even smaller, like maybe 10 to the -5. But just for illustration here, I'm going to add 10 to the -2. So I'm going to add 0.01 to x1 to get kind of my first value here, right? So I'm going to have f of -5 plus 0.01, which will be f of -4.99, 4. And we're going to calculate the value of the function at this location, okay? And we say, you know, when at the original location, -5, 4, the value is 85, okay? So how much did the function change when I added 0.01 to x1, okay? Well, if you add 0.01 to x1 at if you use -4.99 here, you're going to get just a slightly different value, 84.86, okay? So by adding 0.01 to this value of -5, our function changed from 85 to 84.86, okay? And so the partial derivative at that location is going to be -13.99. Basically, it changed by 0.1399 over a change of 0.01. So that becomes a gradient of -13.99, or a partial derivative here. We do the same thing. We need a two-dimensional vector for the gradient. And so we're going to do the same thing by altering x2 by a little bit, right? So we start off at -5, 4. That has a value of 85. What happens if I add 0.01 to 4, right? So now I calculate the function f using -5, 4.01, right? When you go through the calculations, right, and this is just a function of f, if I plug in -5 and 4.01, the result is 85.225. So we go from 85 to 85.225. So that's a change of 0.225. I divide that by how much the small value h that I added. So that gives me basically a gradient of 22.525, okay? And so my estimate of the numeric gradient is -13.99 and 22.525, okay? If I compare this back to slide 10, where I calculated the gradient at -5, 4 using calculus, I got -1422.5, okay? And so we have pretty good match, right? So we would say, okay, this is the analytic answer for the gradient. And here is the gradient that I'm estimating using numeric gradient checking. And we're getting pretty close alignment here. And so this would give us confidence that my analytic answer here of -14 and 22.5 is correct. And I can be confident that using, this solution for the gradient is going to be correct, okay? Or if I used the answer over here using kind of the vector calculus, I'm still getting -14, 22.5. So I would feel confident about my answer here, okay? Because the numeric gradient, it's hard to do, it's hard to mess up, okay? You don't have to do any kind of calculus or any kind of analytics. All you're doing is you're just plugging in a slightly different number. You're going to plug in 5 and 4 over here, and you're going to plug in basically 4.99 and 4. And you just calculate the difference there. And if you're getting something pretty close to what you calculated analytically, you can say, okay, my analytic solution is correct, which is very handy because sometimes the analytic solution is hard and you don't feel confident about your answer. So, all right, that's today's lecture. Let me give you your last view quiz answer for today. Last view quiz answer for today is B. B as in bear. B as in bear is your last view quiz answer. And we'll wrap it up there. All right, have a good night, and we will see you guys on Friday.